All right, here we have a really nice algebra problem from the 2021 Indian National Math Olympiad. We have these two cubic polynomials, x cubed plus ax plus b and x cubed plus bx plus a, and want to find all pairs of integers a and b such that both of these polynomials have only integer roots. So what you might do to start with is try to simplify the problem. Say, for example, if we let a be 0 and then look for a solution. Well, the first polynomial becomes x cubed plus b. Want that to be 0, so that would mean x has to be the cube root of negative b. That's going to be an integer so long as b is a perfect cube. The second polynomial becomes x cubed plus bx. That's always going to have a solution at x is equal to 0. And then the other two solutions are going to be integers if b is negative and if it's the negative of the square of an integer. Now, it seems like that's going to work out so long as b is the negative k to the power of 6 for some integer k, which would give us some solutions. I'll come back and talk about that at the end. But probably what I want to do next is think about this more generally. So what we can do is write x cubed plus ax plus b in this form, x minus p bracket x minus q bracket x minus r. And we can always do this if this polynomial has 3 integer roots. I mean, some of them could be the same and that's fine, but let's say they're non-zero. Expanding out these 3 brackets or using Vieta's formulas, we can write the polynomial in this form. The x squared term would be negative p minus q minus r, or negative bracket p plus q plus r. And that would have to be 0, okay, because there's no x squared term in this polynomial, which gives us r would have to be negative p minus q or negative bracket p plus q. The x term is going to be pq plus pr plus qr, and that's going to equate to our a. And the constant term negative pqr is going to be the b in our polynomial. So we can use that to write expressions for a and b. So it turns out that a would have to be pq minus p plus q all squared and b pq times bracket p plus q. So that's good, but still not obvious like when this is going to have solutions. And in fact, like we need x cubed plus ax plus b to have solutions, also x cubed plus bx plus a. So we need to be able to swap these expressions around as well. For me, this is where I'd try some examples, see if I can notice some patterns. So for any integer values of p and q, there's always going to be an a and b that this works for. So for example, if p is 1, q is 1, we get a is 1 minus 1 plus 1 all squared is negative 3. b is 1 times 1 plus 1 is positive 2. So the cubic x cubed minus 3x plus 2 must have 3 integer solutions. Take another one, say p is 1, q is 2, we get a is negative 7 and b is 6. But what we're looking for in this problem is like to find out whether there's a different pair of integers p and q that gives a is 6 and b is negative 7. Like that we can swap these around and still get a solution. So we'll look at some more examples and see like, can we notice any patterns here as to why or why not we might get any more solutions. So you might notice something about the signs of a and b. What I noticed was b always tends to be larger. Like as p and q get larger, the size of b is getting to be much larger than the size of a. And only in the case where p is 1 is the size of b less than the size of a. So let's try and formalize this and then complete a proof. So as we said, x cubed plus ax plus b we can write in this form. And then r has to be negative p minus q to make sure that there's no x squared term. We can notice that we're always going to have, with 3 roots, we're always going to have 2 that are the same sign. Okay, so without loss of generality, let's say p and q are those 2 integer roots that have the same sign. And let's say p is the smaller of those. So the size of p is less than or equal to the size of q. We have our expressions for a and b that we found earlier. And what we're going to do is show that either the size of b is 1 less than the size of a, which is what we had in those first 2 examples. The size of b is 1 less than the size of a, or the size of b is going to be more than 2 larger than the size of a. And that was basically the case whenever p was larger than 2, or the size of p was larger than 2. Now, if that's the case, then we could never swap a and b, because either b is going to be 1 less, or it's going to be more than 2 greater. So we can't swap a and b and get another pair of solutions. We noticed that A was always negative, and that's going to happen as long as P and Q have the same sign, because P times Q is always going to be positive, and P plus Q squared is always going to be positive and larger than P times Q. So A is always going to be negative. So if A is negative, then B would have to be negative in order that, like, we could have a parent A and B that we could swap. So that means B would have to be negative, so P plus Q would have to be negative, which means both of P and Q have to be negative because we said those had the same sign. Now to prove this first case, that either B is, the size of B is the size of A minus 1, we let P be negative 1. Subbing that in, we find that A is negative 1 plus Q minus Q squared, and B is Q minus Q squared. A and B are both negative, so the size of A, the absolute value of A, becomes negative A, which is 1 minus Q plus Q squared, and B becomes negative Q plus Q squared, so the size of B is in fact 1 less than the size of A. And a second case is going to occur whenever the size of P is 2 or greater. The key for this part is that whenever P is 2 or greater, P times Q is actually greater than or equal to P plus Q. We're going to show that the size of B is always at least 2 more than the size of A. In other words, we want to show that when we subtract size of B minus size of A, we always get something that is 2 or larger. So subbing our expressions in for B and A, we'll get PQ times the absolute value of P plus Q plus PQ minus P plus Q all squared. And then because PQ is greater than or equal to P plus Q, this simplifies down nicely. So we said P was at least 2, and P was the smaller of the two roots, so Q must be at least 2. And this expression must be then greater than or equal to 4. And that agrees with what we showed in our example above. When P is 2, Q is 2, we got exactly B is 16 and A is negative 12. So B is exactly, the size of B is exactly 4 larger than the size of A. As we increase the size of P and Q, they get further and further apart, and the size of B becomes much larger than the size of A. All right, so what have we shown? We've shown that if this first polynomial does have integer roots, which are non-zero, then either the size of B has had to be exactly 1 less than the size of A, or it has to be at least 2 greater. So therefore, if we swap A and B, x cubed plus bx plus A cannot have integer roots, because if the size of B were less than the size of A, it had to be exactly 1 less. But in order for that second polynomial to have integer solutions, we would need the constant term at least 2 greater than the size of B, which gives a contradiction, like these two statements contradict each other. So this is not possible. The only solution to this problem is actually A and B are both 0. Now, originally I thought B being negative k to the 6, or, swapping those around, A being negative k to the 6 and B being 0 would work. Actually, no, because x cubed plus B always has 2 complex roots. And this problem never specified that we are only restricted to real numbers here. So when it says all roots, we have to consider the complex roots as well. So the only solution is 0, 0. Apart from that little trick, I thought this was really quite a nice problem in the Indian Mathematical Olympiad.